In this video, we're going to introduce the idea of a frequency distribution for data and different ways that a variable can be presented and conceptualized across its range of values. Now, there are lots of ways that data can be organized visually in tables or in figures, and there are lots of different guidelines for doing so. People make entire courses just on the visual presentation of data, but we're not going to worry about that. For now, we're going to focus narrowly on what is called a frequency distribution. Okay, let's get started. For this example, let's make a frequency distribution for test scores of 50 different students for whom the scores are whole numbers that range from, say, 52 up to 98. To begin, we take all of those raw scores and place them into groups or class intervals, or as I like to call them, boxes. The frequency is the number of scores that have values in the range of a given interval or box. The score limits are the lower and upper possible observed scores for each interval. Now, the first thing you may notice is that I said my scores range from 52 up to 98, but my groupings or boxes go all the way down to 50 and go up a little higher than the observed scores all the way up to 99. And that's okay. In simple frequency distributions, it's generally best to keep the sizes of the groupings, the width of those intervals, the same, and to have the range of each grouping make some intuitive sense. In this case, I think groupings of 50 to 54 and 55 to 59 and 60 to 64 and 65 to 69 makes more sense than, say, 52 to 58, then 59 to 65, and 66 to 72. Also notice that our score limits in this case are whole numbers that don't overlap at all. That's because we have no fractional scores in our data. Remember, they're all whole numbers. No one has a 94.5. It's either a 95 and you're in the top group, or a 94 and you're in the second from the top group. And that shows the importance of accurately and clearly indicating exactly what the score limits are. If I reported score limits of, say, 90 to 95 for one group and 95 to 100 for another group, where would a 95 go? Is it in the 90 to 95 box or in the 95 to 100 box? That needs to be clear to anyone reading the table. And this is particularly important when we measure continuous variables such as height, those that can theoretically take any value in a range, even if we can't technically measure that precisely. To do this, we also need to keep track of what are called exact limits. Now, let's spend a couple minutes on this point. For a continuous variable like height, score limits are the limits based on our reported values or our rounded values that we're using. If I report my height in whole centimeters, the score limits would be based on values like 172, 173, or 174 centimeters. But my true height, of course, is almost certainly some fractional value in between those whole numbers. And that's where exact limits come into play. If I've rounded height to the nearest centimeter, the exact limits would be halfway between the reported score values. For my example, I might report my height as 173 centimeters, reflecting the score limits, but 103 centimeters would actually include any true value between 172.5 and 173.5. Now, if you're thinking hard on this, you might want to jump in with, yes, but aren't we right back to the problem of what happens when you're exactly 172.5? Would that be a 172 or a 173? In this case, because we're talking about this at a theoretical, conceptual level, the answer is no. Because we're talking about continuous variables, you can just think of that cutoff for the exact limit at 172.5 as being infinitely thin. If a measurement looks like it's 172.5, you just keep going further and further and further beyond the decimal place. You take 172.5 to 172.5000, and sooner or later it'll turn into 172.49999 something, in which case it's grouped with the 172s, or it ends up being 172.500001 something, and you group it with the 173s. Now, of course, you never have infinite precision, but we're just talking about this conceptually and theoretically. Now, exact limits often just reflect our rounding, which makes a lot of sense. But it also implies that they're always halfway between whatever our score limits are. And while that's often true, it's not always the case. Think about when we report that a child reads at the second grade level. Do we mean that she reads between a 1.5 grade level and a 2.5 grade level? Somewhere between the middle of first grade and the middle of second grade? Or do we mean that she reads somewhere between a 2.0 grade level and a 2.99 grade level, indicating that she's reading in the range of second graders? And what about age? If someone says they're 24 years old, are they somewhere between 23.5 and 24.5? Or are they between 24.0 and 24.999? Probably the latter. Now, exact limits can also vary depending on the specific purpose of the measurement. You might think that something like height would always have exact limits halfway between the score limits. A height of 173 centimeters is probably based on rounded values somewhere between 172.5 and 173.5 centimeters. But not always. It doesn't matter if this kid's height is 34.999 inches. He ain't getting on that ride if he's not 35 inches or more. In this case, when they say 35, they mean exact limits of 35.000 or more. 34.5, and he is stuck watching his big sister have all the fun. Now, maybe Disney could hire statisticians to stand in line and explain measurement theory to disappointed 5-year-olds. But I digress. So, for clarity, let's add the exact limits to our frequency distribution table. In reality, you typically don't include both score limits and exact limits in a table, but the exact limits in particular need to always be clear to your reader. Now, another way of reporting the frequency of scores in each interval is to report the relative frequency. This is either reported as a proportion or the percentage of the sample in a given group or class interval or box. Here we've added a column for the relative frequency expressed as the percentage of the total sample. The relative frequency as a proportion is simply the frequency in a given group divided by the total n, while the relative frequency as a percentage is simply the proportion multiplied by 100%. Beyond looking at the frequency within a group or class interval, we often also calculate what's called the cumulative frequency for a group or class interval. Technically, the cumulative frequency is the total number of cases that fall below the upper exact limit of a group or interval. For example, the cumulative frequency for 60 to 64 in this case is 6 because there are 3 cases in the 60 to 64 interval, plus 1 case in the 55 to 59 interval, plus 2 cases in the 50 to 54 interval. Not surprising, we can also express the cumulative frequency as a percent or proportion, just like we see here. The cumulative frequency, technically, for a score, is just the percentage of cases in the distribution that occur below the corresponding upper exact limit for that score. Mathematically, you just take the cumulative frequency for the score or class interval and divide by the total sample size, then multiply by 100%. So let's wrap up this video here. In our next video, we'll shift gears a bit and contrast the cumulative percent and percentile rank. Okay? Bye for now.